Welcome to this A-Level Mathematics exam walkthrough. This is a Pure Mathematics 2 paper from a set of mock papers released in January 2019. You are allowed a calculator and the mathematical formula and statistical tables. As always, the paper and the mark scheme will be linked in the description if you want those. I suggest always having a go at the paper before you watch any of this video. And well, what more do I need to say? Let's just get straight into the questions. Question 1, part A says, given that theta is small and in radians, show that the equation cosine theta takes sine half theta plus 2 tan theta equals 11 on 10 can be written as 5 theta squared take 15 theta plus 1 approximately equal to 0. Okay, so for this we'll need the small angle approximation formulas, and you don't have to memorize these, they are in your formula booklet. So if I pull that up, so these are our small angle approximations. Sine theta is approximately theta, cosine theta is approximately 1 take theta squared on 2, and tan theta is approximately theta when theta is in radians. So we're going to need all of those for this question. So I'll write out the equation they gave us. And now we want to substitute in those small angle approximations. So therefore we would have 1 take theta squared on 2 for cosine theta, and just the angle for sine theta, so that would just be half theta, and the same for tan theta, so this would just be 2 theta, and we can say that's approximately equal to 11 on 10. And now we need to go ahead and simplify this, so you could multiply through by 2, then we would have 2 take theta squared take theta plus 4 theta is approximately equal to 11 on 5. Then simplify and multiply everything by 5. So I might reorder this a little bit. So I'll have the theta squared as the first term and multiply by 5. So that would be negative 5 theta squared. Then negative theta plus 4 theta would be 3 theta. Multiplied by 5 would be positive 15 theta. And we would have that 2 as the constant. 2 times 5 is 10. So plus 10 is approximately equal to 11. Now we're going to have to subtract that 11 from the left hand side, but let's have a quick look at what they were asking us to find up here. We wanted it in the form of positive 5 theta squared take 15 theta plus 1. So what we're going to have to do here is to divide through by a negative 1. So if I subtract that 11 then divide through by negative 1, I'll have 5 theta squared take 15 theta plus 1. Approximately equal to 0, and we have ended up with the approximation they asked us to, and that should be fine for 3 marks there. Part B says the solutions of the equation 5 theta squared take 15 theta plus 1 equals 0 are 0.068 and 2.932, correct to 3 decimal places. Comment on the validity of each of these values as approximate solutions to equation I. So in that case they're referring to this equation up here, which they've called equation I, or equation 1, I guess they're using Roman numerals there. Okay, so, well, remember this is a small angle approximation, so we need the angle to be small, and we're talking about radians, so 2.9 in radians, that's getting close to 180 degrees, so that's definitely not a small angle. 0.068 in radians would classify as a small angle, so this one could be a valid approximate solution. So let's go ahead and see if we can summarize that in a couple of sentences for part B. So I've said here 0.068 is more appropriate as it is a small angle, while 2.932 is not small, so not valid for small angle approximation. You want to be really clear when you're giving these worded answers and not take anything for granted. So in other words, you can't be too obvious in your answers. Okay, so that was question 1 for 4 marks. Question 2 says a curve has parametric equations x equals 6t plus 1 and y equals 5 take 4 over 3t, where t is not equal to 0. Show that the Cartesian equation of the curve can be expressed in the form y equals ax plus b over x take 1, where x does not equal k, where a, b, and k are constants to be found. So this is a fairly standard kind of substitution question where you need to rearrange one equation and substitute it into the other. So if I take this equation for x and make t the subject, we would have x take 1 divided by 6. So t is going to be x take 1 divided by 6. Then what we want to do is plug that into the equation for y and simplify that into this form. Okay, so let's go ahead and substitute it in. We would have y equal to 5 take 4 on 3 times x take 1 on 6. Then simplify. That 3 and that would cancel, so we'd end up with x take 1 on 2 in the denominator there. So just another line of working out. And then if I simplified this fraction here, it would be 2 times 4 over x take 1. So this would become 5 take 8 on x take 1. And then to combine those fractions, multiply 5 by x take 1. And then the denominator would be x take 1. And then simplify this top line, so expand out those brackets. We would have 5x take 5 take 8 all over x take 1. And then negative 5 take 8 is negative 13. So this would simplify to 5x take 13 all over x take 1. And now let's go back to the question. In this case, we would have a equal to 5, b equal to negative 13, and x is cannot equal 1 in this case, because then the denominator would be 0 and the solution would be undefined. So we also need to state x is not equal to 1. All right, there we go. That was question 2 for 3 marks. Question 3 says a curve has equation y equals x squared plus kx plus 14 take 8 on x take 5, where k is a constant. Given that the curve has a stationary point P where x equals 3, part A says show that k equals negative 8. So for this, you need to know what it means to have a stationary point. That means that the derivative will be 0, so the slope of the curve will be 0, so this will be a local minimum or a local maximum. So we need to take the derivative and then let it equal 0 and solve for k. Firstly, I'll just write out that equation, and we need the derivative of this, so dy on dx. And we can use the power rule for most of this, so x squared, the derivative of that is 2x. Derivative of kx is just k. 14 will disappear. And then 8 over x take 5. I should have written that as multiplied by x take 5 to the power of negative 1. Makes it slightly easier to think about, because then we bring that power down the front. That becomes a positive 8. And then take 1 from the power. So this would be x take 5 to the power of negative 2. And we do need to think about the chain rule, but because it's just x take 5 in the brackets, the derivative of that would just be 1, so we don't need to include that. But you should be aware that typically you multiply by the derivative of the function inside the brackets. Okay, we have the derivative now, so then I would generally state the stationary point is when dy and dx equals 0, and they've told us at point P x equals 3. So we also know at point P x equals 3. So therefore, let's plug x equal to 3 into this and let it equal 0 and then solve for k. So we would have 2 times 3 plus k plus, now I might write this as 8 over 3 take 5 squared, and this equals 0. So then we have 6 plus k plus, this would be 3 take 5 is negative 2, squared is 4, 8 divided by 4 is 2, equals 0. So then k is going to equal negative 8. All right, so we have our value of k to be negative 8, which is what they asked us to show. Part B says determine the nature of the stationary point P, giving a reason for your answer. So basically a stationary point can be a local minimum or a local maximum. We just need to find which one it is. To do that, there are a few things we could do. You could find the second derivative, or you can find some values around that point and see what's happening to the derivative as we go either side of that stationary point. So I might just do it that way. So let's just write down this derivative again. And let's say when x equals 2, let's find the slope or the gradient. So let's plug that in. This would be 4 take 8 plus 2 take 5 would be 3. So that would be 8 on 9, and then this would equal 4 take 8 is negative 4, plus 8 on 9 would be negative 3 and 1/9. So the main point there is that it's negative. So the gradient, a negative gradient would look like this, and then when x equals 4, let's find when x equals 4, dy on dx equals 2 times 4 is 8, take 8, plus 4 take 5 is -1, so this would just be 8, and the key point there being that it's positive. So we've gone from a negative gradient to a positive gradient, therefore the curve is going like this, and that would be a local minimum. So I'm going to go ahead and summarize that in a couple sentences. So dy on dx, or the gradient, goes from negative to positive, therefore the stationary point is a local minimum. Part C says show that the curve has a point of inflection where x equals 7. A point of inflection is where the slope stops increasing or decreasing and starts going the other way. So let me see if I can draw a quick example. So if we looked at this graph, the point of inflection would be in here somewhere. So before that point, the slope is decreasing. So if we took this point here and then looked at this point here, that's clearly a steeper gradient than this one. And then after the point of inflection, the gradient starts increasing again. So the point of inflection is where that change happens. And to find that point of inflection, we take the second derivative, and the second derivative is equal to 0 at the point of inflection. Now, again, I said that this can also happen at a minimum and maximum, so we're going to have to make sure it's not one of those, and we need to make sure that it is actually a point of inflection. And because we don't have the graph, usually when they ask this type of question, they'll give you a graph, and in that case, you don't really need to decide if it's minimum or maximum, but when you don't have the graph, you need to do that extra step. All right, so let's get started on part C down below. So as I said, we need the second derivative, and if we look at the first derivative, well, we need to use the power rule again. Well, we would have 2, that 8 would disappear, and then we would have, well, this would be -2, so if we brought that down the front, then this would become -2 times 8, so actually this would be -16 multiplied by x take 5, take 1 from the power, so -2 take 1 would be -3. So that's our second derivative there. 2 take 16 times x take 5 to the power of -3. Then let's find the second derivative when x equals 7. So plug that in. Then we would have 2 take 16 divided by 2 cubed. 2 cubed is 8, so 16 divided by 8 is 2. So then we just have 2 take 2, which is equal to 0. So we do have a point of inflection at x equal to 7. As I said, we need to check it's not local min or max. So what we could also do is to find the derivative at x equals 7. And you have options there. You can find the third derivative and find what that is equal to. You can also find the points around this point of the second derivative as well. So there's a few options here, but I'm going to find the value of dy and dx at x equals 7. So plug that in to dy and dx. That was 2x take 8 plus 8 over x take 5 squared. So here we would have 14 take 8 plus 8 divided by 2 squared. 8 divided by 4 would be 2. So then this is equal to 6 plus 2 would be 8. So the derivative, the first derivative at x equals 7 is 8. Therefore, we know the gradient is not 0. So it's not a stationary point of inflection. It's a non-stationary point of inflection. So therefore, we can say there is an inflection point at x equals 7. Part D says the curve passes through the points 4.5, 14.25, and 5.5, -15.75. Jane uses this information to write down the following. As there is a change of signs, the curve cuts the x-axis in the interval 4.5, 5.5. Explain the error in Jane's reasoning. Well, one reason is we don't know that this graph is continuous through those points. They haven't given us a diagram for this question, and they haven't told us it's continuous, so that would be my answer there. So the curve may not be continuous through that interval. So the curve may not be continuous through interval 4.5, 5.5, so not defined at x equals 5. And that was question 3 for a total of 9 marks. Question 4 starts off with a diagram, and it says figure 1 shows a sketch of part of the curve of the equation y equals f of x, where f of x is equal to x cubed take 6x squared plus 7x plus 2. The curve cuts the x-axis at the points P, Q, and R as shown in figure 1. Okay, P, Q, and R are there. The coordinates of Q are 2, 0. Write f of x as a product of two algebraic factors. Okay, so if it says the curve cuts the x-axis at Q, then it could be said that the x-coordinate at Q would be a root of that function, and therefore we know one factor of this function already. It would be x take 2. So that's the factor theorem. So for part A, we know that f of 2 equals 0. Therefore, x take 2 is a factor. Therefore, we could write f of x as x take 2 times some quadratic. Now you could write this as ax squared plus bx plus c, but if we think a little bit ahead and we look at this function up here, x cubed takes 6x squared plus 7x plus 2, well, the coefficient of x cubed is 1, therefore the coefficient of this quadratic in here, the x squared term, must be 1 to get 1x cubed. Then we would have sum b, and we can also work out c, because that's the other constant, and c times negative 2 must equal positive 2. So what times negative 2 equals positive 2? That would be negative 1. Okay, so now we just need to find a b here. One way you can find a b is to equate coefficients. So pretend like you're expanding this out and then look for the x squared term. So if I did expand this out, what would turn into an x squared? Well, it would be negative 2 times x squared. So we'd have negative 2x squared, and the other x squared term would be x times bx. So this would be plus bx squared. And if we go back to the function, the original function, we have a negative 6 as the coefficient of x squared. So once we expanded this out, the coefficients would have to be equal. So we would have these coefficients, negative 2 plus b, and that would have to be equal to negative 6. So then, therefore, we could say negative 2 plus b equals negative 6. So then b is equal to negative 6 plus 2, which is negative 4. Now, there are plenty of methods to do that. If you want to look around and find a particular method that suits you, just search factorizing cubics, and that should give you a lot of different options. But now we have the value of b, therefore we can say f of x is going to equal x take 2 multiplied by x squared take 4x take 1. Okay, so that was part A. Part B says find, giving your answer in simplest form, the exact x-coordinate of P and the exact x-coordinate of R. So the other solutions to this curve will be when we factorize this quadratic, let that equal to 0, and then find the roots of this quadratic. That will give us the other roots of the cubic, or in other words, the values of P and R. So let's go ahead for part B and let this equal to 0. So x squared take 4x take 1 equals 0. Now we can't factorize this, so we'll have to use a quadratic formula, or we could use the new method that I went through in a recent video. So I'm going to try and use that and see if I can remember how to do it. So I'm going to try to do this without the quadratic formula. So it involves firstly taking the coefficient of x. So we say the sum equals the negative of the coefficient of x. Then we say the solutions are half of this plus u and half of this take u. Then we multiply those together. We say the product needs to equal this product here, negative 1. So we would have 4 take u squared equals negative 1. Then we solve for u. So u squared is going to equal 5. And then therefore u equals the square root of 5. And now our solutions are, well, for x equals 2 plus root 5 and 2 take root 5. Okay, I'm pretty happy that I remembered how to do that. So solving without the quadratic formula there, you could also go ahead and use the quadratic formula there. You should get the same answer. So at R, let's go back and look at the graph. So clearly 2 plus root 5 is going to be larger or greater than 2 take root 5. So let's go back and look at the graph. P is the smaller value and R will be the larger value. So R is going to be 2 plus root 5. So let's say at R x equals 2 plus root 5. And then at P x equals 2 take root 5. Okay, so that should be all done for part B. Part C says deduce the number of real solutions for theta between negative pi and 12 pi to the equation sine cubed theta takes 6 sine squared theta plus 7 sine theta plus 2 equals 0, justifying your answer. Firstly, let's recognize the connection between parts A, B, and C. So this function here is similar to this one here. We've replaced the x's with the sine function. So we found the solutions to this function already. They will be the same as the solutions to this one down here. So we'll use that connection for part C to start off with. So let's say, well, let's firstly write down that function. And we know the solutions to this already based on parts A and B. So the solutions will be when sine theta equals 2 and these two as well. So 2 plus or minus root 5. And we could just make a note that's from parts A and B. Now we need to think about these solutions. What does it mean when you have sine theta equal to 2? Well, the sine function is only defined between the values -1 and 1. So we could say this sine function, sine theta, is undefined for those two solutions that are greater than 1. So undefined for sine theta equal to 2 and 2 plus root 5. They're both greater than 1. Therefore, the solutions to that would be undefined. So the only other option is to take root 5. And if you put that into a calculator, you notice it is less than 1. So let's just go ahead and do that quickly. 2 take root 5. That is negative 0.236. So in between -1 and 1. So therefore, sine theta is equal to 2 take root 5. And it might make it clearer if we actually write down that decimal answer to this. So this will be equal to negative 0.236. Let's just leave it at that. So negative 0.236. Actually, I didn't need that approximation symbol. Okay, so let's continue with this now. What does that mean if sine theta equals negative 0.236? Well, the sine function is negative in quadrants 3 and 4. So we would have two possibilities here. We would have the angle in quadrant 3 and the angle in quadrant 4. So this is what we would call our reference angle or our principal value. Well, actually theta would be our reference angle. So we need to go ahead and find theta, and we're going to have two possibilities between 0 and 2 pi. So let's go ahead and find theta first. We would have the inverse sine of that number. So inverse sine of that previous answer. So it's actually very similar, negative 0.23831. So let's write that down. So this would actually be our reference angle in here. Now let's just go back to the question quickly and reassess. So they've asked us to deduce the number of real solutions for theta between negative pi and 12 pi. So let's go back to our diagram again. So what does this mean if we have these two angles between 0 and 2 pi? So if we start at 0 and go around to 2 pi, we would have this solution here and then this solution here. So, well, to find the actual angle, we would probably be doing pi plus theta and then 2 pi take theta, but we don't actually have to figure out the solutions. We just have to figure out how many solutions there would be. So if we went around, as I was saying, from 0 to 2 pi, there'd be two solutions. So around from 2 pi to 4 pi, there'd be another two solutions. So each time we go up by 2 pi, we would have two solutions. And the interval for the question was negative pi to 12 pi. So if we did that 6 times, right, 2 pi each time to get to 12 pi, then we would have 12 solutions up to 12 pi. Then also we need to go backwards from 0 to negative pi, and we would have 2 solutions in that interval as well. So we would have 12 solutions up to 12 pi and 2 solutions from 0 to negative pi. So again, we don't have to figure out what those solutions actually are. We just have to count how many there were. So my answer there would be 14 solutions. So I might just write down a bit of reasoning behind my answer and then give the answer. So I've written 12 solutions between 0 and 12 pi and 2 solutions between 0 and negative pi. So therefore 14 solutions for theta. And I also just want to point out this was our reference angle or principal value. Okay, so that was part C for question 4. And just taking a look at the marks again. Part A was 2, part B was 2 marks, and part C was 2 marks for a total of 6 marks. Question 5 starts off with a graph, and it says figure 2 shows part of the graph with equation y equal to f of x, where f of x equals 7, take the absolute value of 3x, take 5. The finite region R shown shaded in figure 2 is bounded by the graph with equation y equals f of x and the x-axis. And part A says find the area of R, giving your answer in simplest form. Okay, so if we look at this graph, hopefully you know what shape that is. That is a triangle. So to find the area of a triangle, we need the base and the height. So how can we find the base? Well, we can find where this graph cuts the x-axis. In other words, when y equals 0. And then we can find the y value at the maximum of this graph. So that's what I'm going to go ahead and do to find the area of this shape. So let's start off with the x values where the graph cuts the x-axis. To do that, we'd say, well, let's firstly write down f of x down here. So this is 7, take the absolute value of 3x, take 5. Then let this equal to 0. Add that 3x, take 5 to the other side. So we would have 3x, take 5 equal to 7. To get rid of those absolute value symbols, we want to let the other side equal positive or negative 7. So then we'd have 3x, take 5 equal to positive or negative 7. And then solve for x in these two different situations. So firstly, add 5 to positive 7. So we would have 3x equal to 12. So x would equal 4. And we would also have 3x equal to negative 7 plus 5. So then we'd have negative 2. So then x equals negative 2 on 3. Okay, so we can see that makes sense because we have a positive 4 that would line up with this solution here, and this negative 2 on 3 would line up with this one over here. So our two solutions for x are 4 and negative 2 on 3. Therefore, our base would be 4 and 2/3, right? So that's the distance from the origin. So we just need to basically add those two distances together if we're thinking in terms of distances. We also need the maximum. Well, how would we get the maximum f of x? Well, that would be when this is 0, right? If we're taking the absolute value, then we want the smallest value this 3x take 5 could be would be 0. Any other value, and you're taking the positive of it, so we would have 7 take some amount, and that would be less than 7. So therefore, the maximum of f of x will be 7. So we have the height of the triangle. The base is 4 and 2/3. So let's say the area then is equal to 4 and 2/3 as an improper fraction would be 4 times 3, which is 12, plus 2 is 14 on 3. That's the base, times the height is 7, and then divide that by 2. Another way of writing that is just 7 on 2. So now we need to evaluate this expression. We could do 14 divided by 2 is 7. 7 times 7 is 49. So we'd have 49 and 3 for that area. And we don't have any units, but you could write units squared if you like. So that is our area for part A. Part B says the equation 7 take the absolute value 3x take 5 equals k, where k is a constant has two distinct real roots. Write down the range of possible values for k. So for this one, we can interpret this graph. So you'll notice if we go anywhere above this graph here, well, this graph would not have any solutions. Doesn't matter what you plug in for x, you will not get a y value. So anywhere up here, there won't be any solutions. Now at the point, at the very tip of this graph, there would be one solution at the maximum. So to get two solutions, we need the graph at any point below this maximum, right? So therefore, well, if we drew a line here, what would you call that line? Just at the maximum, at the point, you would call that line y equal to 7, right? We already worked out that maximum. So therefore, if we were to write that in equation form, we would say this graph is equal to, well, k would have to be less than 7 for this to have two solutions. So for part B, we just really needed to interpret that graph there to say k needs to be less than 7, not less than or equals to, otherwise you'd only have one solution. So it must be less than 7 to have two solutions. All right, that was question 5 for a total of 5 marks. Question 6 gives us a function f of x equal to 2 plus kx to the power of -4, where k is a positive constant, and it says the binomial expansion of f of x in ascending powers of x up to and including the term in x squared is 1 on 16 plus ax plus 125 on 32x squared, where a is a constant. And part A says find the value of a, giving your answer in simplest form. So hopefully you recognize we're going to have to use the binomial expansion formula here on f of x, and that formula is actually in your formula booklet, so you do not have to memorize that. It's under the binomial series. So to perform a binomial expansion, we need the brackets in the form 1 plus ax. Now what they don't actually include in this formula in the formula booklet is a coefficient of x, but you can add a coefficient in there and it doesn't make it too much more complicated. So anyways, let's go ahead and write a few things down for part A. So firstly, we have f of x equal to 2 plus kx to the power of -4. And what we want to do is to get that first number to be a 1. So we'll have to factorize something out of this so that we have that 1 as the first term in those brackets. So we could write this as 2 multiplied by 1 plus k on 2x. So I've factorized 2 out of both terms. And all of that is still to the power of -4. So then this would equal 2 to the power of -4 multiplied by 1 plus k on 2x to the power of -4. So both of those terms in those larger brackets are raised to that power. Then we want to perform this expansion on this part of this expression, so this 1 plus k on 2. First, I'm going to write down that formula. So it looks like this in a more simplified version, if you like. So we can have 1 plus ax to the power of n, and this will equal 1 plus... Now, I also kind of want to decode this formula in the booklet, so when you pull this out, you can sort of decode it yourself as well. So again, it doesn't have that coefficient, but when we have nx, we can just write that as nax. So that coefficient is written next to the x for each term. Then we have n times n take 1, n times n take 1 over 2 factorial, which they've written as 1 times 2, that's 2 factorial. And then we have ax squared for the third term there, and that goes on. So if you were to have an x cubed, you would have n times n take 1 times n take 2 over 3 factorial multiplied by ax cubed. And actually that is this whole term squared. So I should have put brackets around that to be clear. So that's ax all squared. All right, so hopefully that makes a bit more sense if it's written that way. So now let's take this expression, this 1 plus k on 2x, and perform that expansion. So we always start off with 1 plus n. N in this case is -4. A is k on 2. and then x. Then we have plus all of this. Now, a slightly easier way to write this divided by 2 factorial is just multiply everything by a half. So a half times n, which is negative 4, times n take 1. Negative 4 take 1 is negative 5. And that is multiplied by k on 2x all squared. So k on 2x all squared. Okay, so we only had to go up to the third term there, the x squared term. So now let's go ahead and try to simplify this. So this could be written as 1 take, this would turn into a negative. 4 divided by 2 is just 2, so this would then be 2kx. And looking at this term now, we would have negative 4 times negative 5, that would be positive 20. Divided by 2 would be 10, and then we would have k squared on 2 squared. 2 squared is 4, so we would have 10 on 4, so plus 10 on 4 k squared x squared. Okay, so that's for that part of the expression, but remember we also have this 2 to the power of negative 4 for the whole thing. So if we go back to this one here, 2 plus kx to the power of negative 4, we can write an expression for that now using this. So this is going to be this multiplied by 2 to the power of negative 4. Okay, so let's just write that out first. And actually another way of writing 2 to the power of negative 4, well, what is that equal to? That's 1 over 2 to the power of 4. 2 to the power of 4 is 16. So we could write that as 1 on 16 multiplied by all of this. So if we expand those brackets out now, 1 over 16 times 1 is 1 over 16. Subtract 1 on 16 times 2. Well, that would cancel with that 16. That would become 1 on 8 kx. And then we could simplify this one here. Divide the numerator and denominator by 2. Then it would be 5 on 4 times 8. So we would have 5 on 8 times 4 is 32 k squared x squared. All right, now let's go back to the expression they gave us. Well, we have that 1 on 16, so that's a good sign. Then we need to let this coefficient, 125 on 32, equal to 5 on 32 k squared. So the coefficient of x squared, let those equal to each other. So therefore, 5 on 32 k squared equals 125 on 32. Then it's actually pretty clear what k equals. 5 times k squared needs to equal 125. So k squared then must equal 25. Therefore, k equals 5. And we don't have to worry about the negative solution because they tell us k is a positive constant. All right, so now we have the value of k. We can find a. So a is going to equal negative 1/8 multiplied by 5, which is negative 5 on 8. All right, so that was part A. So find the value of A in simplest form. Negative 5 on 8 is in simplest form. So that was part A done. Part B says determine, giving a reason for your answer, whether the binomial expansion for f of x is valid when x equals 1 on 10. All right, there's a pretty standard test for validity for this binomial expansions. So for part B, let's actually go back, and now we have the value of k. We can find this expression. So k equals 5, so this would be 5 on 2x. So we can write this expression as 1 plus 5 on 2x to the power of negative 4. This is what we did the expansion on. So for this to be valid, we look at that ax term. So let's just write down to be valid. 5 on 2x, that needs to be between negative 1 and 1. Sometimes that's written as the absolute value of ax, like this. But you can write it like this as well. So then if you kind of solve this for x, if you like, then you get the values of x. Or you can plug in the value they give you. So they say, how do you know it's valid when x equals 1 on 10? We'll then say when x equals 1 on 10, 5 on 2x, plug 1 on 10 into that, we would get 1/4. And that's clearly between negative 1 and 1. So therefore, this value of x is valid. So which is valid? All right, so that was part B. for 1 mark and question 6 for a total of 6 marks. Question 7 gives us a figure and it says figure 3 shows a plot of part of the curve with equation y equals f of x, where f of x equals 2 over x, take e to the power x plus 2x squared. The curve cuts the x-axis at the point A, where x equals alpha, and at the point B, where x equals beta, as shown in figure 3. And part A says, show that alpha lies between negative 1.5 and negative 1. Okay, so let's have a look where A is up here, and that's where x equals alpha. So to show that there is a root there, or that the graph cuts the x-axis, we can find f of negative 1.5 and f of negative 1, and if the signs change, if f of x goes from positive to negative, then we can say that alpha lies between those two values. Okay, so for part A, firstly let's write down f of x, and now let's find f of negative 1.5. So plug that in for x, we'll have 2 over negative 1.5, take e to the power of negative 1.5 plus 2 times negative 1.5 squared, and if we put that into a calculator, we get 2.9435, etc. So I'm just going to write down 2.94, and then we want to do f of negative 1. So if we plug negative 1 in, we'd get negative 2, take e to the negative 1 plus 2, negative 1 squared is just 1. So then let's put that into the calculator, and we get negative 0.367879, etc. Okay, so let's just write that down. Okay, the important point here is that f of x has gone from a positive value to a negative value, so we can say the signs change and therefore a solution exists. So signs change, and to answer the question, I guess we should state therefore alpha lies between those two values. Okay, so that was part A. Part B says the iterative formula x sub n plus 1 equals negative square root of half e to the power of x sub n, take 1 over x sub n, with x sub 1 equal to negative 1 can be used to estimate the value of alpha. And BI says find the value of x sub 3 to 4 decimal places. Okay, so we're going to have to use this iterative formula to find x sub 3. Let's go ahead and firstly write this down below, and x sub 1 is negative 1. Okay, so for part I, we wanted, well, first we have to find x sub 2 and then x sub 3. So you want to aim here when you're doing these types of iteration questions, you want to aim to just put the formula in once and then use the entry key to make it a bit quicker. So let's firstly enter this whole thing, and when we get to x sub n as the power, we want to put in negative 1, and same for this denominator of this fraction here, negative 1. Double check to make sure you've entered everything correctly, and if you have a newer calculator, it may be easier to do this with the fraction button, and I get an answer of negative 1.088 and so on. So I might just write down negative 1.088, and then what you do not want to do now is to clear your calculator and get rid of that whole thing you just entered. What you want to do is to do the entry button, try to find the entry button on your calculator, and that'll bring up that formula again. And then all you have to do is go to where x sub n is in that formula and delete whatever is in there, and then insert the answer from your previous calculation. And what that is going to do now is it allows you to iterate over and over with your calculator without having to enter any additional information. So it's going to take the previous answer and perform the calculation, and then it will do that over and over again for you. Okay, so let's go ahead and find the x sub 3, the value of x sub 3. That's negative 1.0428. So I'll just write down those first 5 figures. So negative 1.0428. And the question said round off to how many? 4 decimal places. Well, actually, I've basically already done that, but Let's just write that as negative 1.0428 rounded off. Okay, so we found x sub 3. And then for part 2, the question says, find the value of alpha correct to 2 decimal places. So what we've been doing here is to iterate to find alpha. So we have an approximation for alpha with x sub 3. And if we keep iterating, we'll eventually get to a point where we can get alpha correct to 2 decimal places. So for part 2, we want to keep doing this iteration. Get your calculator up again and just keep doing this. So go entry, enter, entry, enter, and you should notice something about the decimal places as you go on. So let's do a few more. It doesn't matter how many you do, you could just keep going on forever, and it should keep getting more and more accurate. But what we want to see here is, you notice my previous 3 answers here, negative 1.056, negative 1.058, negative 1.057, they are all going to round off to negative 1.06. So if we do a few more here, just to get the point, negative 1.057, that would again round off to negative 1.06, another one. And once you get to the point where, because they said round off to 2 decimal places, once you get to the point where you're always getting the same answer to whichever accuracy they're asking you to, then you can say this is negative 1.06 to 2 decimal places. So alpha is equal to negative 1.06 2dp. Okay, that was part B2. And on to part C. Says the value of beta lies in the interval 1.53. A student takes 3 as her first approximation to beta. Given f of 3 equals negative 1.4189 and f dash of 3 equals negative 8.3078 to 4 decimal places. Part C says apply the Newton-Raphson method once to f of x to obtain a second approximation to beta. Give your answer to 2 decimal places. Okay, so for part C, we need to use the Newton-Raphson method. And let's go ahead and write down the values they gave us. Okay, so the Newton-Raphson method formula is in your formula booklet under numerical methods. So luckily that's one less thing you have to memorize. So let's just go ahead and write this down. So the Newton-Raphson method says the next iteration, x sub n plus 1 equals x sub n, take f of x sub n divided by f dash of x sub n. And here we had x sub 1 equal to 3. So they've given us x sub n, which is 3. They've given us f of x sub n, or f of 3, and f of dash of 3. So they've given us everything. All we need to do is to substitute that in to find x sub 2, or the second approximation. So let's go ahead and just write that down with everything substituted in. So we would have 3 take these values up here, and actually those negatives would cancel out, so we just have 3 take this. So let's go ahead and put that into our calculator, and we get 2.8292, and it said round off to 2 decimal places. Well, firstly, I would write that down to a few decimal places past what we need to round off to. So 2.8292, and then round it off to 2.83. Okay, so that was part C. And part D says a different student takes a starting value of 1.5 as his first approximation to beta. Use figure 3 to explain whether or not the Newton-Raphson method with this starting value gives a good second approximation to beta. For this question, you actually kind of have to understand how the Newton-Raphson method works. And if we go back to the figure, remember for part C, we took an approximation of 3, which I guess would be over here somewhere because f of 3 was a negative. So x equals to 3 would be over here. So what if we took x equal to 1.5? Well, the way the Newton-Raphson method works is basically we draw a tangent to the curve at whatever approximation we start with. So if we try to draw a tangent to this curve, and this doesn't have to be too accurate for this particular question, because based on how the curve is shaped, you can see the tangent is going to shoot off way in this direction, and it's not getting anywhere near this solution here at B. So if, for example, we took 3 as our first approximation, now this is a bit trickier, but you can see that when you draw the tangent at wherever 3 is exactly, I'm not sure exactly where it is, but you can see that it falls within that range between the 3 and the point where the curve cuts the x-axis. So that's what you want with the Newton-Raphson method, because what happens next, and I'll show you with the other tangent because it's a bit hard with that one. What happens next is you take this value, and that basically becomes your next approximation as to where the curve is cutting the x-axis. So in this case, once we got to this value, then what happens is you go back up to the curve and you want some f of this value. So if we called this x sub a, for example, or x sub 2, whatever, then we would want to go up to the curve and then find an f of x sub a. In this case, well, if it's cutting the x-axis here, we're not going to get that. There wouldn't be any solution to that f of x. Now, if I've somehow drawn this tangent wrong, even if it cut over here, then we'd go up to this curve and we'd end up probably finding a solution for, or an approximation at A. So this solution 1.5, or this approximation at 1.5, is not going to help us in terms of the Newton-Raphson method, because we would end up getting a second approximation that is nowhere near our solution at B. So to use the graph, firstly I would draw this tangent. That would be my first step. Then I would indicate, well, there's no solution of f of xa, has no solution, or it's not in that interval between 1.5 and b. So we could also say f of xa is not in the interval 1.5, 3. So it needs to be in here somewhere, so you end up actually getting an approximation closer to b, not further away or on some other part of the curve. So therefore 1.5 is not a good first approximation. Okay, so that was question 7. Part A was 2 marks, part B was 2 marks, C was 2 marks, and D was 2 marks. Question 8 starts with a figure and it says a circle with center 9, -6 touches the x-axis as shown in figure 4. And part A says write down an equation for the circle. For this question, you need to know what they refer to when they say the circle touches the x-axis. So the only type of line that can touch a circle is the tangent. So this means that the x-axis must be a tangent of this circle. Therefore, we know if we were to draw the center of this circle and draw a radius from that center to the x-axis, they would meet at 90 degrees. What does this mean? Well, it means that this radius must be parallel with the y-axis if they are both 90 degrees to the x-axis. And so also they've told us this center is at 9, -6. So that means this y value over here would be at -6, and we know the radius would have a length of 6 units. So we know the radius is 6 units. We have the center, and therefore we can write down the equation of a circle as long as we know the general equation of a circle, which is x take h all squared plus y take k all squared equals the radius squared. And here the center equals hk, and r represents the radius. So all we need to do is input the values we are given. So we know the center is 9, -6. So this will be x take 9 all squared plus y plus 6, because k would be a negative. So this negative in here becomes a positive. So y plus 6 all squared. And then the radius squared, we've just said the radius is 6, so 6 squared is 36. Okay, so that's your equation for that circle. Part B says a line L is parallel to the x-axis. The line L cuts the circle at points P and Q. Given that the distance PQ is 8, Part B says find the two possible equations for L. Let's go back to the diagram then. Firstly, we know any line parallel to the x-axis has an equation y equals k, k being a constant. So for example, if this horizontal line cut the y-axis at 2, this would be y equals 2. Now let's assume we had a horizontal line going through the center of the circle. Now we know the center was at 9, negative 6. So this line would be at negative 6 on the y-axis. So that equation would be y equals negative 6. Now we don't have a line going through the center. And by the way, if that line did go through the center, this distance between where it cut the circle would be 12, 2 lots of the radius. What we do have, what they've given us, is a line where that distance is 8. Okay, so somewhere up here, that distance would shorten and it would become 8 between where it intersects the circle. So we have a distance there of 8. Now we don't know whether it's above the center or below the center. So it could also be a straight line down here. Now, of course, it would be equal distance from the center of the circle because we know the distance would be the same. And what we're actually looking for here is that distance away from the center. If we can find that, then we can find the equation. It would be negative 6 take some value or negative 6 plus some value. So is there a way we can find that distance between the center and this line? Yes, there is. It's the distance between the center and the chord. So using that formula, we can find that distance and then the equation of the line. And that distance from the center to a chord comes from the idea of turning this into a right angle triangle. Also, I should note, we are looking for the perpendicular distance because that would be the distance from the y-axis at negative 6 to where the line cuts the y-axis. That would be the perpendicular distance. So we're looking for the perpendicular distance from the center to the chord. Therefore, we could turn this into a right angle triangle. And we know about the circle theorem that says the perpendicular to the chord also bisects the chord. So this distance then is half of 8, which is 4. This is the distance we're looking for. We know this one is 6, the radius. So using that idea, we have that formula for the distance from the center to the chord. So let's go ahead and work that out. So for part B, we have distance from the center to the chord equals the square root of the radius squared, which is 6 squared take 4 squared. So this is going to be 36 take 16, which is, well, let's just write that down, which is the square root of 20. Which we could simplify if you broke this up into 4 times 5. The square root of 4 is 2, so you could simplify this to 2 root 5. So then we have the equation of those lines. Let's go back to the diagram to make this really clear. We know this distance here is 2 root 5, or up here as well is 2 root 5. So then this line is going to be y equals negative 6 plus 2 root 5. That would effectively be this value on the y-axis, and then this one's going to take that value as well. So therefore we have those two equations. So let's go ahead and write those down. Take 2 root 5 and y equals negative 6 plus 2 root 5. Okay, there we go. That was question 8. Part A was 3 marks and part B was 4 marks. Question 9 says the amount of antibiotic, y milligrams, in a patient's bloodstream t hours after the antibiotic was first given is modeled by the equation y equals ab to the power of t, where a and b are constants. And part A says show that this equation can be written in the form log y equals t log b plus c, expressing the constant c in terms of a. So the logical first step for me for part A is to take the log of both sides. So we start off with y equals a b to the power t. Then if we take the log of both sides, we'll have log y equals log ab to the power t. Then we can use our log laws to say that log of a times b will be the log of a plus the log of b to the power t. And I'm not writing the base 10s, but all of these logs are base 10. So this is log a plus log b to the power t. And then we can use another log law to say log b to the power t equals t log b. Okay, so the two log laws I've used there are log ab equals log a plus log b, and log of a to the power x is equal to x log a. Okay, so we'll finish off with log y equals t log b plus log a. And let's just double check what they wanted us to show. They want us to show that it equaled log y t log b plus c, and then express c in terms of a. Well, in this case, c is going to be log a, log base 10 of a. Okay, so that was part A. Part B says, a doctor measures the amount of antibiotic in a patient's bloodstream at regular intervals for the first 5 hours after the antibiotic was first given. She plots a graph of log y against t and finds that the points on the graph lie close to a straight line passing through the point 0, 2.23 with gradient negative 0.076. Estimate to two significant figures the value of a and the value of b. For this question, you need to recognize the connection between this equation here and the equation of a straight line y equals mx plus c. So you'll notice, if we like, this log y could be equivalent to y in this equation, and c in this case matches up to c in this equation, which we also know is the y-intercept. So for this question, they're telling us the line passes through 0, 2.23, which we also know is the y-intercept, right? 0 on the x-axis must be the y-intercept. So going up to this equation again, making that connection between c and the y-intercept. Therefore, we know c will equal 2.23. And remember what c is. C was log a. So we'll be able to say log a equals 2.23. All right, so I'm going to write down as much of that information as I can. So the point they gave us, the gradient was negative 0.076. Then let's write down the equation as well, and the form that we are saying this essentially matches up to, so y equals mx plus c. All right, now you don't have to write all this down in your exam. I've always got in the habit of writing all of the information from the question down to help out with my solution and give it a more logical flow and to make it more complete as an answer. But again, you probably don't really need to write all of this. Okay, remember what we said? We said log a equals the y-intercept. T is the variable, log b is our gradient. So log b is equal to our gradient, negative 0.76, and log a is equivalent to our y-intercept, which is 2.23. Then actually here I'm going to write the bases because it makes the next step a bit easier to see. So to find that unknown b, we take this base and we kind of pretend we're like going around in a circle sort of thing, and we say, well, b now is going to be 10 to the power of this, and the same for log base 10 of a. That's going to be, so a is going to equal 10 to the power of 2.23. Okay, so then b equals 10 to the power of negative 0.076, and a will be 10 to the power of 2.23. And then we can get our answers for a and b, and we'll be fine. For b, I get 0.839, etc. 0.839. And for a, I get 169.824, etc. And I just want to double check, it said round off to two significant figures. So to round these off, this is going to round off to 0.84, and this will round off to, 9 rounds the 6 up to 7, so this will be 170. Okay, so that was A and B for part B. Part C says, with reference to this model C part I, give a practical interpretation of the value of the constant A. And part 2 says give a practical interpretation of the value of the constant B. This is where I would go back to read the start of the question to get a picture of the context again. Because after all of that working out, I've usually kind of half forgotten about what the question is actually asking or talking about. So this says the amount of antibiotic in a patient's bloodstream T hours after the antibiotic was first given. And the first equation we actually started with was y equals AB to the power T. Now we have a value of this A and B, we can interpret what they actually mean. So for example, if T was equal to 0 in this equation, B to the power 0 would be 1, we'd just be left with y equals A. So when we have 0 hours, then A is the amount of antibiotic. So in other words, A would be the initial injection of antibiotic, or the initial amount of antibiotic at T equals 0. Then if we think about what happens with B, so at 1 hour, we would have A times B. At 2 hours, we'd have A times B times B. 3 hours, we'd have A times B cubed. So B then is going to be the amount that the antibiotic is reduced per hour, because T is in hours. All right, so let's go ahead and try to write some of that down for part C. And again, we're looking at this equation, the starting equation. And remember, we're talking about antibiotics. So A, we said, was the initial amount of antibiotics. So A is the amount of antibiotics at T equals 0 at the start of the experiment, or injection, or whatever you want to refer to this as. And so e.g. initial dose of 170 milligrams, because we got that value for A. Then for part 2, that was part 1, part 2, we'll say B is the rate that the antibiotics break down. And then if we look at the value we got for B, 0.84. So if you multiply something by 0.84, you could say you had 84% of that thing, or you can also say it's reduced by 16%. So that's what I'm going to say. So e.g. 16% reduction per hour. Okay, so that's part C. Part D says use the model to estimate the time taken after the antibiotic was first given for the amount of antibiotic in the patient's bloodstream to fall to 30 milligrams. Give your answers in hours correct to 1 decimal place. So for part D, now I guess you could use y equals AB to the power T, or the log equation with the logs in it. I feel that this may be easier with using the log equation, because then we won't have a power. It will just be basically linear in effect. So I'm going to use that one. So we've got y equals 30, and we need to find t. And let's write down the equation we had. So log y equal to the gradient, which was negative 0.076 times t, plus the log of a, which was 2.23. So that's the model we can use. If y equaled to 30, we would have log of 30 equal to negative 0.076 times t plus 2.23. So then we're going to get negative 0.076 t equal to log 30 take 2.23. And then we're just going to have to divide that by negative 0.076. So let's go ahead and put this into a calculator. Log of 30. Now this will be automatically base 10 in your calculator. Subtract 2.23 and then divide all of that by negative 0.076. And we get 9.906, etc. So t equals 9.906. And it's said to round off to correct to 1 decimal place in hours. So it's already in hours. So we just need to say t is approximately equal to 9.9 hours. So if we were to interpret that, we would say it took 9.9 hours for the antibiotics to fall to 30 milligrams in the patient's blood. Okay, so that was part D. Part E says comment on the reliability of your estimate in part D. Well, remember our answer for part D was 9.9 hours, and go back to part B, it said the doctor measures the amount of antibiotic for the first 5 hours. So this this question or this answer we got is extrapolating, and the problem with extrapolation is that it goes beyond the data and therefore inherently it becomes less reliable. So for part E, we can say it's not reliable for those reasons. So we are extrapolating. So for part D, we were extrapolating beyond the data for the first 5 hours and assuming the rate that the antibiotics reduces remains constant. Also, we do not have enough evidence to deduce that the model is still valid after that initial 5 hours. So therefore, it is an unreliable estimate. Okay, so that was part E. For question 9, part A was 2 marks, part B was 2 marks, part C was 2 marks, part D was 2 marks, and part E was 1 mark. We are up to question 10. And by now you might be thinking this is actually a test of reading comprehension and not mathematics, because a lot of the questions so far have been quite wordy. But I guarantee you this is a mathematics exam, not a reading comprehension exam. But anyways, question 10 says, a biologist conducted an experiment to investigate the growth of mold on a slice of bread. The biologist measured the surface area of bread A centimeters squared covered by mold at times t days after the start of the experiment. Initially, 9 centimeters squared of the bread was covered by mold, and 6 days later, 56.25 centimeters squared of the bread was covered by mold. In the biologist's model, the rate of increase of the surface area of bread covered by mold at any time t days is proportional to the square root of that area. By forming and solving a differential equation, part A says show that the biologist's model leads to the equation A equals 3/4 t plus 3 all squared. One of the most important pieces of information here is that the rate of increase of the surface area of bread is proportional to the square root of that area. And remember, they told us the area we're calling A centimeters squared. Also, they tell us the initial area covered and the area covered 6 days later. With all of that information, we are going to be able to come up with this equation down here. So let's get started on that for part A. Now there is a little trick to this that actually shows up quite a bit in A-level exams, and I'll show you how to do this. And also there is a question similar to this in the specimen papers that I've been through as well. So firstly, let's state a few things. Let's say A is equal to the surface area covered by the mold, and we're also told when t equals 0 days, the area is 9 centimeters squared, and when t equals 6, A equals 56.25 centimeters squared. And we are also told the rate of change of the area is proportional to the square root of that area. So one way we can represent the rate of increase of the surface area is dA on dt, and this is proportional to the square root of that area. To turn this into an equation, we can introduce a constant, call that k root a. So dA on dt is equal to k root a. That's the first key step. And here comes the little trick you can do, or the little algebraic manipulation you can do. You can say now, if you multiply the right hand side by dt and divide by square root a, you can end up with this equation, dA on the square root of a, which I might write as a to the power of a half, which is the same thing as the square root. This is equal to k dt. So I've rearranged that equation by multiplying and dividing. Next, what we want to do is take the integral of both sides. So we would have the integral of a to the power of a half. Actually, another way to write this is 1 on the a to the power of a half, dA, which could also be written as a to the negative a half, dA, and the integral of k dt will just be integral of k dt. So these two expressions are equivalent, right? Hopefully you can see that. Next, let's evaluate these integrals. The integral of a to the power of negative a half, we can use the power rule. Remember, we add 1 to the power and then divide by that power. So if you divide something by a half, it's the same as multiplying by 2. So this is going to be 2a to the power of a half. And on the right hand side, we'll have kt, right? We need to introduce that variable if we just have some constant, and then we'll have some constant on the end. Now, you don't have to really write that on both sides. You can just do it on one side. Then we have essentially the equation that's going to help us get to our answer. So 2 root a equals kt plus c. So that was the little trick to get us to this point. Then using this information up here, so t equals 0, a equals 9, we can find c. So if we substituted those values in here, if t equals 0, this term would disappear. A equal to 9, the square root of 9 is 3. So then we would just be left with c equal to 6. All right, so now we have the equation 2 times root a equals kt plus 6. Next, let's use the other piece of information we're given, t equal to 6, a equal to 56.25. Substitute that into this equation to find k. So we would have 2 times the square root of 56.25 equal to k times 6 plus 6. Again, because they told us when t equals 6, a equals 56.25. Then if you solve this, well, okay, the square root of 56.25, let's figure out what that is. 56.25, we get 7.5. 7.5 times 2 is 15, take 6 is 9. So, okay, we'd have 6k equal to 9, and then therefore k is going to be 9 on 6. Divide both by 3, we'd get 3 on 2. All right, so now our equation is 2 root a equal to 3 on 2 t plus 6. This is a good time to revisit the question and remember what expression or equation they're asking us to find. We're asking to find this equation in terms of a, so let's go back. All we need to do now is to rearrange this in terms of a. So firstly, divide by 2. So if I divided both of those terms by 2, I'd have root a equal to 3 on 4t plus 3, 6 divided by 2. And then to get rid of this square root, I could square both sides. So then I would have a equal to all of this, 3 on 4t plus 3 all squared. And let's just double check that is what they were asking us to find. Okay, so again, that is a useful trick to know how to get from this idea of proportionality, introducing a constant and then rearranging the differential equation a little bit to get to whatever they're asking you to get to. Part B says the biologist's full set of results are shown in the table below. So here we have t days going up to 30 and the area going from 9 to 330 odd. Use the last 4 measurements from table 1 to BI, evaluate the biologist model, and B part 2, suggest a possible explanation of the results. All right, what I might do is just for the sake of this video, copy this table and paste it down below so I don't have to keep scrolling up. Okay, so we have this table and we want to evaluate the model and then suggest a possible explanation for the results in the table. So when it says biologist model, they're actually talking about the equation that we've found. So we need to evaluate the data in terms of this model here. So for part I, we're given t and a, so you could either plug a in and find t or plug t in and find a. I might do it plugging t in. And remember it says the last 4 measurements. So we only need to do the last 4, we don't need to do the first 2. So starting at t equal to 12, let's find a. A would be 3/4 times 12 plus 3 squared. 12 divided by 4 is 3. 3 times 3 is 9 plus 3 is 12. 12 squared is 144. So the first area we get 144, which is pretty close to 143.78, the actual measured area. So we can say this is approximately equal to 143.78. Next, t equal to 18. The area would be 3 on 4 times 18 plus 3 squared. I might go to the calculator for that one. So what's 3/4 of 18? 0.75 times 18 plus 3 and square that, I get 272.25, and this is approximately equal to 271.19. So for those two measurements, the model's doing pretty well. Next one, t equal to 24. Area would be 3/4 times 24 plus 3. 24 divided by 4 is 6 times 3 is 18 plus 3 is 21. 21 squared is 441, which is not approximately equal to 334.81. So we could say it's greater than 334.81. And then t equal to 30 is our last one we have to check. 3/4 of 30 plus 3. Let's go to the calculator. We get 650.25, and that's clearly much larger than 337. So again, I'm going to revisit the question. So it's asking me to evaluate the biologist's model. So far I have compared the model to the measurements, but in order to evaluate it, I want to also interpret what these results mean. So the model is working pretty well for t equal to 12 and t equal to 18. So that's the first thing I would state. And remember, you can never be too obvious when you are asked to interpret or evaluate certain things with mathematical models. Always kind of try to overanalyze and say, well, okay, the model works well for these two. If you notice that, then state that. Next, we noticed the model did not work very well for t equal to 24 and t equal to 30. So what might be happening? Well, the model is giving an overestimate, and the actual area seems to be flattening out around 340, 330, 340. So perhaps that's reaching a maximum. And the question, remember, was talking about bread, I think it was. So the surface area of bread, perhaps the total surface area of bread is around 340 centimeters squared. So let's say that the model is giving an overestimate for A. So the model appears to give an overestimate for A when t equals to 24 and 30. And next, that was part I, or part 1. 2 said suggest a possible explanation for those results. Well, as I was saying, perhaps the area reached a maximum, which is not built into the model. The model itself is not accounting for the fact there may be a maximum area. So let's just try to state that in a sentence or two. So the results indicate an upper limit for A, but the model does not give an upper limit. Perhaps mold reached max area, e.g. the bread became completely covered. I think the key point there is stating you recognize that that area seems to be flattening out at a certain maximum area, and the model does not account for that. Okay, so that was question 10 for a total of 9 marks, 6 marks for part A and 3 marks for part B. Question 11 starts off with a figure, and it says figure 5 shows a sketch of the curve with equation y equals f of x, where f of x equals sine 2x over negative 3 plus cosine 2x, and x is between 0 and pi. The curve has a minimum turning point at P and a maximum turning point at Q as shown in figure 5. And part A says show that the x-coordinate of P and the x-coordinate of Q are solutions to the equation cosine of 2x equals 1 over 3. Okay, so here we have the curve, and P and Q are minimum and maximum. So firstly, let me point out that you should know when you're looking for minimum and maximum of a curve, you'll need the derivative. So we're going to be looking for the derivative of this function to find P and Q. So let me just get started by writing some things down here for part A. Turning points when f dash equals 0. Then I'm just going to write the function down here. So if we're looking for the derivative of a function and it has a function in the numerator and denominator, that usually indicates we want to use the quotient rule. So there's lots of things you can actually do with this function. You could use the double angle formula and maybe simplify it a little bit. You could use some other trigonometric identities to maybe manipulate this expression somehow. But I would say a good start before you do any of that is just start with the quotient rule and see what you get. So firstly, let's write down the quotient rule. So the quotient rule says if we have a function with a function in the numerator and denominator, and I've called those u and v, you could call those g of x and h of x or something, then the derivative f dash will be v multiplied by the derivative of u, subtract the derivative of v times u, all over v squared. And this is in your formula booklet on page 6 here. It has under differentiation the quotient rule there. So it's not something you need memorized for A-level mathematics. And so let's go ahead and apply this rule to this function. So we'll have f dash equal to v, which is the denominator. So negative 3 plus cosine of 2x. So I'm putting brackets around that to indicate that I'll be multiplying all of that by the derivative of u. So the derivative of u will be the derivative of sine 2x. The derivative of the sine function is the cosine function. And we also need to use the chain rule on that 2x inside the sine function. So the derivative of 2x is 2, and that will be multiplied by cosine 2x. And then we subtract the derivative of v. It will be the derivative of this denominator here. So the derivative of the cosine function is negative sine. So again, we need to use the chain rule on that cosine 2x. So we'll have 2 times negative sine 2x. So because that's a negative, this will actually turn into a positive in the middle here. So we'll have plus 2 sine 2x. And we multiply all of that by u, which is just sine 2x. Okay, and then we have all of that divided by v squared. So the denominator all squared. So we've performed the quotient rule on this function. Now we want to try to simplify this down to cosine of 2x equals a third. So next step would be, for me, would be to expand these brackets, and then also looking at this sine 2x, we could write that as sine 2x squared. So firstly, expanding those out, we would get negative 6 cosine 2x plus cosine 2x times 2 cosine 2x would be plus 2 cosine squared 2x plus 2 sine squared 2x. And looking at those cosine and sine squared, you might be seeing where this is going already, but let's keep trying to simplify this. I might leave that denominator as is because we're going to let this whole thing equal to 0. And actually, I could have done that in this line. So I might actually change that now. So then remember, we're saying at the turning points, all of this equals 0. So then let's multiply by this denominator on the right hand side. So effectively making it disappear. And then let's divide through by 2 as well. So divide the numerator or everything by 2, and then we would get negative 3 cosine 2x plus cosine squared 2x plus sine squared 2x equals 0. And now here we have the identity cosine squared plus sine squared. That is 1. So we can write this as negative 3 cosine 2x plus 1 equals 0, and then subtract 1 from the right hand side, and then divide by negative 3. We would have cosine 2x equals negative 1 over negative 3. The negatives would cancel out, so we'd be left with 1 over 3 on the right hand side. And if we go back to the question once again, we'll see that is what we were looking for. That's the equation we were looking for. So there we go. We have shown that the x-coordinate of P and Q would be the solutions to this equation. Part B says, hence find to 2 decimal places the x-coordinate of the maximum turning point on the curve with the equation y equals f of 3x plus 5. And part 2 says y equals negative f of a quarter x. And we have different domains for each of those. Okay, so let's start on part 1 or part I, f of 3x plus 5. You need to understand your graph transformations for this question. You need to understand what effect this 3x has on the graph of this function and on the derivative. Actually, it doesn't really matter what this effect has on the graph. We're actually really only concerned with the derivative because that's going to tell us the x-coordinate of the turning point. So when you multiply the input by 3 in the function, what you're doing is also multiplying the input of the derivative by 3. So we can say at the turning point, it will be the cosine of 6x equals a third. Because we just take that 2x, multiply it by 3, and that's the solution for the turning point. So we'll start off there. So therefore, at the turning point, the cosine of 6x equals a third. Let's start by finding our reference angle or our principal value by taking the inverse cosine of a third. So 6x is going to equal the inverse cosine of a third. Put that into a calculator, making sure your calculator's in radians, and you should get 1.23095, etc. So let's write down that to a few decimal places. Well, maybe 1.23 is good enough. So 1.23. That's, as I said, the reference angle or principal value. So one way to help us picture this is to draw a unit circle. And because the cosine of a third will actually have two solutions, because the cosine function is positive in two quadrants of the unit circle. It's the first quadrant and the fourth quadrant. If you think of the cosine function as the x-coordinate here, you know x-coordinates are positive in this direction over here to the right of the y-axis and negative over here. So the cosine function is positive in the first and fourth quadrants, and we have a reference angle of 1.23, and that's radians, so it'll be less than pi on 2, so somewhere up here perhaps. Anyways, this is just a diagram, so it doesn't have to be accurate. So that would be our reference angle for six lots of x, and as I said, we have two solutions to this, and we'll also have that reference angle in the fourth quadrant here. Now that is our reference angle in there, but the actual solution will be all the way around the outside from 0 all the way around to this line here created by that angle. So this will be our solution all the way around here, that angle out there, and our first solution would be in here for 6x again. So let's go back to the graph actually first. So remember, the question is asking for maximum turning point. Here you need to interpret the graph. Q is the maximum here, and it's the second turning point or the second solution to this derivative. I want to try to be really clear here. The derivative is going to equal 0 at P and Q. So we're going to get two solutions, and we want the second one here for the maximum. The first one will be the minimum, the second one will be the maximum. So going back to our question now, as I was trying to point out, this would be our first solution, this first angle. This second one, created by the reference angle, would be the second solution or our maximum turning point. So how do we find that angle around there, around the outside? Well, remember, this is also like, if I replace that x, you can also think of this as 0 radians and 2 pi radians. Just like over here, this is pi radians. So if this is 2 pi radians, we can do 2 pi, subtract the reference angle, and we would get this solution out here around the outside. So for our solution for 6x for the maximum turning point, we want to do 2 pi, take the reference angle. So for this statement, I just want to say this would be, the solutions to this would be 1.23 and 2 pi, take 1.23, etc. So there are our two solutions. Keeping in mind our domain is between 0 and pi on 3. So you could keep going here. You could say the next solution would be 2 pi plus 1.23. And depending on what that turns out to be, once we divide by 6, it may fall within the domain, but we don't care about that, remember, because we only want the maximum, which is this second solution. So this is what I'm going to go up to. So then let's state we want the second solution. So the second solution is the maximum, therefore x equals this 2 pi take 1.23 divided by 6. And once we solve this, we should have our answer for the x coordinate. So let's do 2 pi take our previous answer and then divide that by 6. and that is between 0 and pi on 3. Remember to always check your domain, just in case. So our final answer here will be, and I believe the question said round off to 2 decimal places, so our final answer will be 0.84. So let's just write out a few decimal places, 0.842, which rounds off to 0.84. Okay, so that was part BI, the x-coordinate for the maximum. Then let's go back. So the second one was y equal to negative f of a quarter x. Again, think of your transformations. What effect does this negative have on the function? Looking at the graph, the negative will essentially reflect the graph in the x-axis. So this graph would now be looking like this. And actually, the input has also changed, so that quarter would have an effect, probably increasing the period. But I'm not too concerned about what the graph would look like. I'm more concerned about the effect on the minimum and maximum. So the important point is that the negative of the function will reflect it in the x-axis. So then, because we're looking for the maximum, now our maximum is the first solution. So rather than looking for the second solution like we did in the part 1, we're looking for the first solution now. And we also need to keep in mind the fact that we're dividing by the input by 4. So we have to divide the input of the derivative by 4. Okay, so for part 2, then that derivative, cosine 2x equals a third, becomes cosine of 2x divided by 4. Well, 2 divided by 4 is a half. So this would be cosine of x on 2 equals a third. Actually, I want to write down the function we're looking for as well. So then we can say x on 2 now equals the inverse cosine, which we've already found to be 1.23, and so on. And again, because we're looking for the first solution, we don't have to worry about all this unit circle stuff. We can just say, well, we know this is the first solution. To multiply that by 2, we'll have our solution for x. So we had the inverse cosine of 1/3 multiplied by 2 gives us 2.46. And we don't have to round that up. So our final answer there to 2 decimal places, 2.46. Okay, so that was part B and question 11 for a total of 8 marks. Question 12 says a company extracted 4,500 tons of a mineral from a mine during 2018. The mass of the mineral which the company expects to extract in each subsequent year is modeled to decrease by 2% each year. And part A says find the total mass of the mineral which the company expects to extract from 2018 to 2040 inclusive, giving your answer to 3 significant figures. A similar question to this appeared in the specimen papers as well. And I quite like these questions because as long as you recognize you need to look at this as a geometric sequence, the method here is actually quite straightforward. So for part A, we're going to use the geometric series formula. And the reasoning is we're starting with an initial amount of 4,500 tons. And then we multiply that by, well, how do you decrease something by 2%? You multiply it by 98% or 0.98. That would be our multiplier. So to get the next year's minerals extracted, we would multiply this by 0.98. Then the next year we'd do the same thing. So it's a geometric series. You're multiplying by the same thing each time. And then to find the sum of all those, we're going to use that sum formula for a geometric series. So once you recognize that, this should be fairly straightforward. So let's write down some of the information. So we have the mass in 2018 equal to 4,500 tons. We have a decrease of 2% per year or per annum. And the number of periods or the number of years, can be a little bit tricky, but if we just think of this as 2018 to 2040, well, that would be 22 years. But when it says inclusive, we have to include 2040 as well. So it's kind of like 2018 to 2041, if that makes it any clearer, but basically it's just 22 plus 1, so 23. So our time or number of years is 23. And then let's write down the sum formula for a geometric series, and that is something you do not have to memorize. So that is in your formula booklet under geometric series, S sub n equals A, all of this. So let's go ahead and write that down. So A multiplied by 1 take R to the power n all over 1 take R, where R is the ratio between each term. In other words, what you're multiplying by. So as we said, that's 0.98 to decrease by 2% per year. Then our A is our initial amount, and we have to plug all of those in. So 4,500 multiplied by 1 take R to the power n, so 0.98 to the power of 23, divided by 1 take R, well 1 take 0.98 would be 0.02. Then essentially we're just plugging this into a calculator. So 4,500 multiplied by 1 take 0.98 to the power of 23, and then divide that by 0.02, and we get 83,621.86. 152. And this is where I would do a quick reality check or common sense check. So if we're extracting just a bit more than 4,000 tons per year for 23 years, we'll just multiply that by 4 firstly. Well, roughly 20 times 4 is 80. And okay, if we start at 4,500, we might expect to get more than 80,000 tons. But remember, this is decreasing by 2% each year. So this might then drop below 4,000. So around 80,000 would be what you should expect. If you get something way off 80,000, then that would be a point where you could say, okay, my answer is probably not correct. Maybe I haven't plugged this in correctly. But something close to 80,000 should, satisfy that common sense check. And then go back to the question. It said also to round off to 3 significant figures. So we want to round this to 836. 6 is the third significant figure, and that will stay the same. So this will be 83,600 tons. 2 3 significant figures. Okay, that was part A. Part B says find the mass of the mineral which the company expects to extract during 2040, giving your answer to 3 significant figures. Okay, so for part B, we're going to be using essentially the compound interest formula. Remember, with the compound interest formula, you can calculate, say if you invest, $2,000 in an account, the compound interest formula lets you calculate how much you would get out of that after a certain number of years. So you would multiply this by 1 plus the rate to the power of the number of periods, or the time that you invest. And so the A there standing for the amount that you get out. So if we apply that same logic to this problem, we're decreasing the amount per year, but it's still compounding because it's 2% of the previous year. And what we want is the amount in the 23rd year. So 2040 would be the 23rd year after they started. My apologies there. That should be 22, of course. So the periods there is 22 because we're not including that year in an amount. It's just the year we're going up to. So yes, 22 makes sense. Then we'll just calculate this. So 4,500 multiplied by 0.98 to the power of 22. And we get 2,885.268 and so on. So let's just write that down first. And then again, we wanted to round that off to 3 significant figures. So to 3 significant figures, well, the 8 is the third significant figure that would round up because of the 5. So this is going to be 2,890 tons. That would be the amount extracted in 2040. Okay, that's part B. Part C says the cost of extracting the mineral each year are assumed to be £800 per tonne for the first 1,500 tonnes, £600 per tonne for any amount in excess of 1,500 tonnes. The expected cost of extracting the mineral from 2018 to 2040 inclusive is X million pounds, And part C says find the value of x giving your answer to 3 significant figures. Okay, so if we have 800 pounds per ton for the first 1,500 tons each year, and we have 23 years, we would have 23 times 1,500 tons at 800 pounds per ton, and then 600 pounds per ton for the rest. So let's work out how many tons we are extracting at 800 pounds per ton. This would be 23 times 1,500. That's 34,500. And so now let's do a bit of a calculation for our cost. Well, firstly, we're going to have 34,500 tons at 800 pounds per ton. That would be the cost for that amount. And we need to add on the cost for the rest. For the rest, we're going to have the total tons take 34,500 multiplied by 600. So 600 pounds per ton multiplied by, now for this I might use the unrounded number to make it more accurate. So we would have 83,621 take 34,500, and that should give us the total cost. So let's plug that in, and we get an answer of 57 million and 73,116.91. So why not write all of that down firstly? So 57 million approximately, and then it said to 3 significant figures. So rounding this off to 3 significant figures, well, this 0 is going to round up due to the 7, so this would be 57.1 million. And that is the final answer for part C. And all up, question 12 was a total of 7 marks. Question 13 says, figure 6 shows the curve with parametric equations x equals 6 cosine t and y equals 5 sine 2t. The finite region R shown shaded in figure 6 is bounded by the curve, the x-axis, and the line with equation x equals 3. Use calculus to show that the area of R is 20 take 15 on 2 root 3. So the first thing we need to do is to relate x to y somehow, and we can do that by relating the integral of y with the derivative of x. So let's get started. The first thing I want to do here is to find the derivative of x, so dx on dt. So if we're looking for the derivative of 6 cosine t, we need to know the derivative of the cosine function, and that is negative sine t. So the derivative of this is going to be negative 6 sine t. Then we want to, well, we're looking for the integral of y under that curve, and we want it with respect to x. We won't get that if we take this integral, that will be with respect to t. So we can start by saying, well, we're looking for the integral of y dx. Another way of writing this is the integral of y times, if I introduce a dt on dt here, this would be dx on dt times dt. So essentially multiplying by 1, dt on dt. And this would be equivalent to, or another way of writing it is, well, let's insert y. Y is 5 sine 2t. So the integral of 5 sine 2t multiplied by dx on dt, which we just found, negative 6 sine t. And then we have that dt on the end. So now we're looking for this integral with respect to t. This is equivalent to the integral of y dx. So even though we are taking the integral with respect to t, it's effectively the same thing as taking the integral of y dx. The first thing I would probably do with this is to use the double angle formula for this sine 2t, because these have different variables at the moment, 2t and t. I want them to be the same to make it easier to integrate. So we know that sine 2x is equal to 2 sine x cosine x. So that's one of the double angle formulas. So we can simplify this one here to, well, take that sine 2t and insert 2 sine t cosine t. So this would be 5 times 2 sine t cosine t. Next, we could remove all of the constants. So 5 multiplied by 2 multiplied by negative 6, it's negative 60, get rid of that, or in other words, take it out the front. And then I have a sine t multiplied by sine t, so that's going to be sine squared t times cosine t dt. Here we have the integral of two functions multiplied together. Usually that indicates we want to use a u substitution, and this took me a while to think what I want to substitute u for. So should u be cosine t or sine t? But as I go through it, perhaps I can point out why it should be sine t, not cosine t. So firstly, let's say u equals sine t, and not sine squared either. So because then du on dt equals cosine t. That's the derivative of the sine function. So now we have the derivative equal to this function here. If we did sine squared t, the derivative would actually be 2 cosine times sine. So then it wouldn't work out so nicely. So now because the derivative is just cosine t, we can rearrange this to say that du equals cosine t times dt, which is this function on the end. So then this becomes negative 60 multiplied by the integral of u squared multiplied by du. And we know how to take that integral using the power rule. So we add 1 to the power and also divide by that power. So then this becomes negative 60 multiplied by a third u cubed plus some constant c. Then simplify, 60 divided by 3 is 20, so this would be negative 20 multiplied by u cubed. Now we could substitute sine t back in for u here, which I think I will do. This is now going to be negative 20 times sine cubed t plus c. So we have now this integral y with respect to x, which is the area under the curve. And now we want to find the definite integral from 0 to x equals 3, but remember this is in terms of t now, so we're going to have to find what t equals when x is 0 and when x is 3 to find the bounds of this area. So, well, let's do that down below. So we're looking for when x equals 3 and when x equals 0, what are the values of t? And we could do that by substituting x into this equation here. So if x was 0, well, we would have 6 cosine t equal to 0. So actually, let me rub that out. So we'd have 6 cosine t equal to 0. So then cosine t equals 0 divided by 6. And so what is the solution when the cosine function is 0? That is when t is 90 degrees and 270 degrees, or in this case, we're talking about radians, that would be pi on 2. And let's look at the domain of t again. Well, t is between 0 and pi on 2, so the only solution there for t would be pi on 2. So t equals pi on 2. Then let's do when x equals 3. We would have 6 cosine t equal to 3. So then cosine t would equal 3 divided by 6, or 1/2. And when do we have the cosine function equaling 1/2? If you're quite good with your absolute values, then you'll know that already. But if you are struggling to remember, you could remember these useful triangles. So we have pi on 3 and pi on 6 in it. And that the lengths of that triangle are 1, 2, and root 3. So when we have the cosine of pi on 3, we have the adjacent over the hypotenuse, which is 1/2. So then t is going to be pi on 3, which also falls within our domain for t. So there are our bounds now, pi on 2 and pi on 3. So now our area R, we can look at. Area R is going to be the integral from 0 to 3 of y with respect to x. And this is equivalent to the integral we've found, which is negative 20 sine cubed t. Negative 20 sine cubed t. And here's a slightly confusing step. Remember, pi on 2 is equivalent to x equals 0. So that is actually our lower bound here. And our upper bound of the area is going to be pi on 3. So pi on 3 is clearly less than pi on 2, but you have to keep in mind how they relate to the x value. So try not to get tripped up there, even though you might think, well, pi on 2 now must be the upper bound of the area. It still needs to equate to the x values. So now we're looking for this definite integral. We need to plug in pi on 3 first. So we'll have negative 20 sine cubed of pi on 3, subtract negative 20 sine cubed of pi on 2, and that should give us the area R. The sine of pi on 3, well, let's go back to our little absolute values triangle. That would be opposite over hypotenuse, root 3 on 2. So we have down here negative 20 times root 3 on 2 cubed. And the sine of pi on 2 is just 1, so this would then be negative 20 multiplied by 1 cubed is just 1. So in other words, that's just going to become negative 20. Let's simplify this expression here. We would have root 3 cubed. Root 3 times root 3 is 3. And then we'd multiply that by root 3. So the numerator there would be 3 root 3. Then 2 cubed is 8. So this expression now would become negative 20 multiplied by 3 root 3 on 8. And then subtract negative 20 is add 20. Then if we simplified this expression further, well, a common factor between 20 and 8 is 4. 20 divided by 4 is 5. 8 divided by 4 is 2. 5 times 3 is 15. So this expression here would simplify to negative 15 root 3 on 2. And I might bring that positive 20 to the front. It usually looks neater if you put the negative in the middle and the positive terms out the front. And then, well, we could combine those two numbers, but let's go back to the question and check. So we wanted to show it was 20 take 15 on 2 root 3, and that is what we've got. So 20 take 15 on 2 root 3. Okay, so that was question 13 for 7 marks. A quick rundown again of the steps. Firstly, we wanted to relate those integrals. So we had to relate the integral of y with the derivative of x to get the integral of y dx. Then we had to use a u substitution. Quite difficult u substitution in my opinion, because you had a lot of options there. You could do sine squared or cosine or sine, and you had to use u equal to sine t, mainly because the derivative is a lot simpler than sine squared, or let's say you let u equal to cosine, you wouldn't get rid of this dt so easily. But when we let u equal to sine t, we end up with du equal to cosine t dt, and that effectively gets rid of that cosine function and makes the integral much simpler. Recognizing what to substitute for u kind of comes with practice. There's no hard and fast rule to say substitute this and not this. But yeah, practice those and get good at recognizing when the u substitution is useful and when it isn't. Then, we also had to use the double angle formula before that, and then we had to find the t values for the values of x, and then do the definite integral. Okay, so quite a few steps there for 7 marks. Question 14 says figure 7 shows the curves with equations y equals kx squared and y equals the square root of kx, where k is a positive constant. The finite region R shown shaded in figure 7 is bounded by the two curves. Show that for all values of k, the area of R is a third. For me, when I first saw this question, I kind of thought it might be a bit nasty, but actually it turns out to be quite nice. So what is the key here? Well, we're looking for this area, and well, firstly you have to recognize, well, that area is going to be the area under this curve, y equals the square root of kx, take the area under the second curve, y equals kx squared. So if we take the entire area under here, subtract this unshaded area under this one, so the one in here, we will get the shaded area R. So once we recognize that, then we realize we have to find this x coordinate here, where the two curves intersect. And that's really the key, I think. So when these two equations are equal, in other words, kx squared will equal the square root of kx, then we'll have this value. Let's call that x1. Okay, so let's start there. Let's say when kx squared equals the square root of kx, we'll have that value for x1. What could we start with here? Well, square both sides might be a good start to get rid of that square root. If we square both sides, we would have k squared times x to the power 4 equals kx. Then if we divided by kx on the left hand side, we would have 1 left on the right hand side. Remember, this is like multiplying by 1. So divide by kx, k divided by k is, k squared divided by k is just k. X to the power 4 divided by x is x cubed, and this would equal 1. Then divide by k because we want to make x the subject of this equation. So x cubed equals 1 on k, then take the cube root of both sides, and we would have x equal to the cube root of 1 on k. Okay, so we have that x value for where the curves intersect and the upper bound of the areas. So then we want to find that area R. Remember, we said it was the area under the first curve, subtract the area under the second curve. So how would we represent that in terms of integrals? Well, we would say area R equals the integral of square root kx in terms of x, subtract the integral of kx squared dx. And this is from 0 to cube root of 1 on k. Then let's think about these integrals. So the integral of the square root of kx, remember k is just a constant, so we can think of this as the square root of k times the square root of x. What's the integral of the square root of x? Well, that's x to the power of a half. We add 1 to that power, divide by that power, and we get 2 root k x to the power of 3 on 2. Remember, I added 1 to half and divided by that. So if you divide by 3 on 2, you essentially multiply by 2 on 3. So 2 on 3, root k x to the power of 3 on 2. And this is from 0 to the cube root of 1 on k. And then we need to subtract this integral here. So the integral of kx squared, that's a little bit easier. We add 1 to 2, that's 3. Divide by 3, we would get k on 3 x cubed from 0 to the cube root of 1 on k. Then let's do the substitution. So if we substitute 0 into either of these, that whole term would become 0 because we'd be multiplying by 0. So all we really need to worry about is substituting the cube root of 1 on k into these expressions. So I might separate this part. So we'll have 2 root k on 3 multiplied by the cube root of 1 on k to the power of 3 on 2. And all of this is subtracting k on 3 and then the cube root of 1 on k cubed. Well, that cube root and that cube are going to cancel out. So that one's not going to be too bad. What about this one over here? Well, remember, something to the power of 3 on 2. If we just do a little example over here, a to the power of 3 on 2 is the same as a cubed to the power of a half. So this is like the square root of a cubed. So if we separate it like this, because we're cubing it, that will cancel with the cube root. All we'd be left with is 1 on k to the power of a half. In other words, the square root of 1 on k, which we can further simplify because the square root of 1 is just 1. So this is actually going to just be 1 over the square root of k. That's what this term here is going to simplify to. This one over here, remember we said those cube roots will cancel, and this would just be 1 over k. Actually, let's just write that, and then we can simplify further in the next line. So I don't want to do too many steps at once. Now looking at this, you can really see it starts to simplify nicely. So this root k cancel with this square root k on the bottom line, and then these two cancel. Next, we just have 2 on 3 multiplied by 1. So this is 2 on 3 subtract 1 on 3. 2/3 take 1/3 is 1/3. Go back to the question. It said show that the area of R is 1/3, and that's what we got. Okay, so again, when I first saw this question, I was kind of like, okay, that looks kind of complicated, but actually it's not too bad once you get into it. All right, question 14 for 5 marks. Question 15 says a sequence of numbers a sub 1, a sub 2, a sub 3, etc. is defined by a sub n plus 1 equals k take 3k over a sub n, where n is any integer, positive integer, and where k is a constant. The sequence is periodic of order 3. Given that a sub 2 equals 2, part A says show that k squared plus k take 12 is equal to 0. For this question, we're going to want to evaluate some of the terms in this sequence and use this idea that it is periodic of order 3 to equate some of those terms and then come up with this equation here. What does this mean? Periodic of order 3, it means the sequence repeats after every 3 terms. So let's start by writing down, well, a sub 2 equals 2, then a sub 3. What would that be? Well, substitute a sub 2 into the formula or the equation up here. So this would be k take 3k on 2. And I might just write that down here to make it a bit easier for myself. Okay, now we can scroll down a bit. So then we're looking at a sub 3. We could perhaps simplify this a little bit. So if we combined those 2 terms, multiply this one by 2, we would have 2k take 3k over 2. 2k take 3k is negative k, and that's over 2. So negative k on 2 for a sub 3. Then a sub 4 is going to be, well, substitute it into this one here. We would have k take 3k over negative k take 2, negative k over 2. Simplifying this, we would flip and multiply that denominator. So 2 times 3k, this would be k take 6k over negative k. So actually this would be positive 6k on k, because those 2 negatives would turn into a positive. And then looking at this term here, 6k on k, those k's would cancel out and we'd be left with k plus 6. So we have a2, a3, a4. If we find a5, that term is going to equal a2. Remember, because it's periodic 3. So every third term is going to repeat. So a sub 5 is going to be k take 3k over the fourth term, k plus 6. If we try to simplify this, we can multiply k by k plus 6. This would be k times k plus 6 take 3k all over k plus 6. And I guess we could simplify a bit further by expanding those brackets. We would have k squared plus 6k take 3k over k plus 6. And then, well, this could also be written as 6k take 3k would be k squared plus 3k over k plus 6. Okay, so we have the fifth term. Now let's say that a5 equals a2. So then we'll have this fifth term, k squared plus 3k over k plus 6 equals to 2. And then we can simplify this and hopefully end up with the equation they were looking for. So multiply by k plus 6 on the right hand side, we'll have k squared plus 3k equal to 2k plus 12. Then bring everything over to the left hand side, subtract 2k, 3k take 2k is just k, so k squared plus k take 12 equals 0. And go back to the question again. They wanted us to show that this would be true, and that's what we've done. K squared plus k take 12 is equal to 0. Okay, that was part A. Part B says, given that a sub 1 does not equal a sub 2, find the value of the sum of the first 121 terms of this sequence. Let's get started on part B down here. Firstly, we're told a sub 1 does not equal a sub 2, and we're looking for the sum of the first 121 terms of this sequence. Well, what I would start with is by looking for a value of k to get some actual values for these terms in the sequence. So start with this quadratic and then factorize this. So 2 factors of 12 that sum to 1 would be 4 and 3. So we could have plus 4 and negative 3. That would make negative 12 and sum to positive 1. So then, therefore, k equals negative 4 or k equals 3. Now, how can we find which value we need to go with, negative 4 or plus 3? Well, here we need to think about this key piece of information. A1 does not equal A2. How can we find A1? Well, we could try to go backwards with this equation or formula here. Another way of doing it would be to say that, well, A4 must be equal to A1 because this idea that this sequence is periodic. So if we find A4, then we'll know A1. So that's a much easier way of finding A1. So let's say A4 is k plus 6. A4 equals k plus 6. And then substitute these values in. Negative 4 plus 6 is 2, or 3 plus 6 is 9. Again, let's revisit that piece of information. A1 does not equal A2. We know A2 is 2. So therefore, A4 must equal 9, and therefore K must equal 3. So therefore, A4 equals 9, as A4 equals A1 and should not equal A2. Then, therefore, we also know that K equals 3. All right, so that's how we're finding the value of K. Now we can find the 3 terms in this sequence. We have A2 and we have A4. We just need A3 to get all 3 terms, because remember, there are only 3 different terms in the sequence. So the next one's going to be negative K on 2. So A3 equals negative K on 2. K being 3, this would be negative 3 on 2. So now we can say, well, we know what the sequence looks like. It will be starting at 9. Remember, A1 equal to A4 is 9. So we start at 9. Then our next term, A2, was 2. Our next term, A3, is negative 3 on 2. And then it starts again at 9. And then 2, etc. Okay, so we have this sequence of 3 terms repeating. Let's look at the sum we were looking for. We're looking for the first 121 terms. And so this is going to be, well, how many lots of 3 go into 121? 120 divided by 3 is 40, plus an extra term. So we would have 40 lots of 9. 40 times 9 plus 40 times 2 plus 40 times negative 3 on 2. And then we'd add on that extra 1, which would be the first term again. So add on 9. Let's evaluate this. 40 times 9 is 360 plus 80. 40 divided by 2 is 20 times negative 3 is negative 60 plus 9. Then what would we have here? 300 plus 80 plus 9, 389 for a final answer for that sum. So let's go back to the question. I believe that's all we needed to find. So find that value. We've done that. Final answer 389. And that was question 15 for a total of 7 marks. And that is the end of the paper. I hope you found that useful. If I made any mistakes or I missed anything, please let me know in the comments, and leave any additional working out or any other strategies you might have used for any of the questions. Please leave those in the comments as well. It's much appreciated. Also, please leave a like if you appreciated this. These A-level papers take quite a bit of work. Subscribe if you want to see more content, and I will see you in the next one. Bye for now.